So let me talk some more about sign of a permutation leading up to even and odd permutations and the alternating group. So the discussion we had last time gives you this theorem. We didn't quite prove the theorem, we sort of indicated why it's true. Showed that there exists a surjective group homomorphism called sign from the permutation group on n letters to this group denoted by plus minus 1. So it's a group with two elements such that sign of the transposition 1 comma 2 is minus 1. So if you just take the flip, that has minus sign. And the identity certainly has the plus sign. That's part of saying that it's a group homomorphism. The identity has to go to the identity. Let me remind you how this was defined. So here's a permutation, an element of S6, written in cycle notation. 1 goes to 2, 2 goes to 5, 5 goes to 3, 3 goes back to 1, and then 4 goes to 6, 6 goes back to 4. Given a permutation, I draw something called its graph. So I say 1 goes to 2, 2 goes to 5, 5 goes to 3, 4 goes to 6, oh, 3 goes to 1, I forgot that, and then 6 goes to 4. That's the graph of this sigma. Once you have this graph, you define something called the crossing number of this sigma, denoted by n sigma. That just counts, that's a number that counts how many crossings are there between these threads. 1, 2, 3, 4, 5, 6 crossings. So the crossing number is 6. And the sign is minus 1 to the power the number of crossing. So the sign of this one is 1 because there are even number of crossings. By the way, one other thing that this graphical notation is good for, it shows you, for example, why these transpositions or flips generate the permutation group, or rather why consecutive flips, like flipping 1 and 2, or flipping 2 and 3, just these guys generate the permutation group. All I do is take this picture for sigma and stretch it out so I have only one crossing at a time. So like I had the thread between 2 and 3 crossing and also the thread between 4 and 5 crossing. I've first done the 2, 3 crossing, then done the 4, 5 crossing. And I've gone down like that, one at a time. What that shows me, if I just draw these lines in the middle, you'll find that I have written this sigma, this same sigma, as a product of transpositions. Here is the transposition 2, 3, flipping 2 and 3. Here is the transposition 4, 5, etc. So 2, 3, then 4, 5. Let's keep reading. Then 1 and 2 crosses, then 3 and 4 cross, then 5 and 6 cross, and then 4 and 5 cross. And I claim sigma is the product of these transpositions. And you see each flip corresponds to one crossing, basically. Yeah. So this actually tells you that that if n sigma is 6, then you can write it as a product of 6 transpositions. So if you can write something as a product of 6 transpositions, then its sign is minus 1 to the power that number. That leads us to this definition on the right. You say that sigma is an even permutation if sigma can be written as a product of even number of transpositions. And I'll say that sigma is an odd permutation if sigma can be written as a product of odd number of permutations. So odd or even if you can write it as odd number of or even number of permutations. Okay, so the one that I have on the example on the left, that one is even because I just wrote it as a product of 6 transpositions. So every transposition is odd. By the way, the transpositions generate the permutation group. So every permutation can be written as a product of transpositions. So every permutation is even or odd. But I'm not saying yet that it cannot be both even or odd. Of course, it's going to turn out that nothing can be both even or odd. In fact, it's going to turn out soon that the even ones are exactly the ones with sign equal to 1, and the odd ones are exactly the ones that have sign equal to -1. And we almost indicated that already. But hold on just a little more, and we'll see that. First, I should note a few more things. Sign of, so group homomorphism means what? Group homomorphism means sign of alpha beta is sign of alpha sign of beta for all alpha beta in the permutation group. So sign of alpha beta alpha inverse is going to be sign of alpha sign of beta sign of alpha inverse, because by the homomorphism property, and then the inverse can be taken out as well. Oops. Then you realize that these three things are just numbers, either +1 or -1, and they certainly commute. So you can move this one here, and then sine alpha cancels with sine alpha inverse, and both of them are 1 or -1 anyway. So what you get is sine of beta. So sine alpha beta alpha inverse is same as sine beta. So conjugate permutations have the same sign. And that implies immediately that sine of tau is -1 if tau is a transposition. Because if you give me a transposition ij and I want to calculate its sign, I'm going to pick sigma such that sigma of 1 is I, sigma of 2 is j. Pick any such permutation that takes 1 to I and 2 to j. And then I claim this is same as that ij is same as, ij is same as sigma 1, sigma 2. But that's same as sigma times the transposition 1, 2 times sigma inverse by what we discussed a little while ago about conjugating permutations in cycle notation. So the sign is same as sign of sigma 1, 2, sigma inverse, but we just proved that that's same as sign of 1, 2, which we know is -1. So every transposition has sign -1. So every transposition is odd. So that tells you, so take sigma in Sn, write sigma equal to tau 1, tau 2, tau k, where tau j's are transpositions. We know we can do that. We did it here, for example, on the left. Just took this sigma and wrote it as a product of transpositions. Do it in any possible way. There are multiple ways of possibly doing it. And do it in any way, then sine of sigma is going to be sine of tau 1 dot sine of tau 2. By homomorphism property, it just multiplies out. but each of these is just minus 1, so it's just minus 1 to the power k. It tells you the sign is 1 if k is even, and if k is even, we call sigma is even. If you can write it as a product of even number of transpositions. And it's minus 1 if sigma is odd. So if it's even, then the sign is 1. If it's odd, then the sign is minus 1. But the sign is a well-defined function. We saw that. It's minus 1 to the power of this number of crossing. So the sign cannot be both plus 1 or and minus 1 at the same time. So no permutation is both even and odd. So that tells you that the permutation group splits into two pieces, even ones, odd ones. These have sign 1, these have sign minus 1. Splits exactly into two pieces. Yeah, so each is either even or odd, but not both. Okay. And it also tells you that if you take two things that are even and take their product, both of them have sign 1, so the product have sign 1. So the product of two even is even. And then the product of two odd is again even because both of them have sign minus 1, so the product has sign 1, which means it's even. And then a product of an even and an odd is again odd. All this just follows from the homomorphism. It's just translation of the homomorphism property. Okay. So I won't write this down, but it's written down in the notes that even times even is even, odd times odd is even, and then even times odd in either order is even. And then the transpositions are odd. You can figure out which cycles are even and which are odd. So like if you take this cycle or that cycle, these are even, but that cycle is odd. You can figure all these things out rather easily. And then finally, these even permutations are the same as the permutations of sign 1. That's called the alternating group. Set of even permutations. In Sn, which is same as all sigma such that the sign is 1. Which is same as the kernel of this homomorphism. Oops, called say sign. Yeah, and this we see is a subgroup of Sn. We'll see it has exactly half the size. It will follow very soon. We can check it by hand directly right now, that if you take the even permutations and multiply by any odd permutation, then you get all the odd permutations. And that immediately implies that there are exactly the same number of things on the left side as the right side. So the size of this group is n factorial over 2. Half of the number of permutations. So half of them are even, half of them are odd. So like if you take S4 or maybe S5, you'll get the identity, you'll get 3 cycles like this, you'll get 5 cycles like this, all this type, all of them of this type, and then all of them of 2 disjoint cycles. These would form A5. It would be a subgroup of S5 of size 60, which is 120 over 2, which is 5 factorial over 2. Okay. There's a lot more to say, but we'll just stop here.